this computer. All right. So here is the problem we did, right? We had a 9.58" casing, 8,000 feet, combination casing string, and the mud density was 12.5 pound per gallon, and the expected formation pressure was 6,000 psi. So this 8,000 feet is the casing set depth. Casing set depths. What happened? Okay, casing set depths, and that's where you wanna basically have the length of your final design casing, and you have only an AD casing. That's the type of casing. Again, AD is 80,000 psi minimum yield strength, right? And use the design factors, design for worst case scenario. We talked about the design factors, 1.8, 1.125, 1.1 for tension, collapse, and burst, right? So we talked about this, and then we started basically doing the burst design, right? So let's go to that part. The burst, simply you calculate, you multiply your pore pressure by design factor, which is 1.1, that is 6,600 psi. That is the burst requirement, right? And then you want to go to the tables and check to see which of the casings that you have in your inventory will satisfy this condition, right? So we have basically an AD casings. What happened? Did we? Yeah. And also let's do the collapse as well, right? And before going to the table. So 0.052 mud weight depth design factor. So for the collapse, we mentioned that we have the casing and this is the wellbore. So you assume that inside is empty, right? And outside is basically the drilling fluid that you have inside, with 12.5 pound per gallon in this case. And then the worst case scenario for the collapse happens at the very bottom because you have the highest hydrostatic pressure, right? So that is the worst possible point, right? For the burst, however, you assume that you have the same constant burst requirement all over the wellbore, from the surface all the way to the bottom, and that is equal to pore pressure multiplied by design factor. So that's a column of gas inside your casing, right? And then the outside is empty. So I should mention this, that again, let's say this is P in and this is P out, right? At any point inside your system, right? This is wellbore, this is your casing, burst pressure is equal to P inside minus P outside, and collapse pressure is just the other way around. This is P outside minus P inside. Now for a worst case scenario, we assume that for the burst, outside is empty, so this is 0. So we just have inside pressure, which is constant, a column of gas. For the collapse, we assume that inside is 0, right? And outside is basically a column of drilling fluid. That is the worst case scenario that could happen, right? And then you see that for the burst, we have a constant burst requirement. For collapse, because it's a hydrostatic, it's 0 at the surface, it's maximum at the bottom. So the highest collapse pressure requirement that you would need is at the bottom, and that's why you would need to use higher grade casings at the bottom of your casing set, okay? If you guys have questions as I talk, just don't hesitate to ask, okay? All right, so this is 0.052, 12.5 pound per gallon, 8,000 feet, 1.125 collapse design factor. So that's 5,850. So we went to the table. These are the casing grades, right? These are the weight of the casings that we have. This is the cross-sectional area of the steel of the casing. And this is the burst requirement, burst pressure, burst rating, I should say, for each of these casings. And this is the collapse ratings, right? So the burst requirement was 6,600 psi. And then we look at the table, we saw that these two doesn't satisfy the burst requirement. So these two are out, right? And then these two satisfy the burst requirement. So we could use either of these two, right? But we also need to check for the collapse. So if you look at the collapse, you will see that this one doesn't satisfy the collapse requirement because your collapse requirement is 5,800 psi, but this one can only resist up to 4,760 psi. Okay, so you have to use this casing for the bottom of your wellbore at least, right? So we mentioned that, okay, so this one satisfies the burst requirement to some, for all depths, right? But doesn't satisfy the collapse requirement. This one, however, satisfy both of these conditions, right? But as we know, collapse is not constant collapse pressure, right? Even for the worst case scenario. For the worst case scenario, you have the highest collapse pressure at the very bottom, right? And then at some point, this collapse basically goes down. The collapse pressure drops. So there is a chance that you can use this casing up to, from the surface up to some specific depths, right? And that is what makes the collapse design a bit more complex than other designs, okay? So please listen carefully how we do this, because this is very important, okay? And that's basically the most complex part of casing design, okay? So now, the question is that you should think about that question is that, okay, now I have two casings that satisfy burst condition, but only one of them satisfies the collapse requirement. Now, there is a chance that I can use the 47 pound per feet casing up to some specific depths, which satisfies my collapse and burst requirement. And I can use the rest of my wellbore at the bottom. I can use this casing, the higher grade casing. So I should have a structure like this. So this is my wellbore, right? I will have a casing here up to some depths that is 47 pound per feet. And then from here all the way to the bottom, which is 8,000 feet, 8,500 feet, I think, or 8,000 feet, this will be 53.5 per feet, right? Now, the question is, what is this depth? What is the depth that I can have 47 pound per feet casing, and the rest will be 53.5. Okay, that's the main question we're trying to answer here. Now, why don't we use these two casings, the first two, 40 and 43.5?
They don't satisfy the burst.
They don't satisfy the burst, so we can never, ever use these two casings. So these are completely out of question. So forget about these two. The only reason that we are trying to add this casing is because it satisfies the burst condition, but doesn't satisfy the collapse. And that's why we can use it for up to some specific depths. Okay. All right. So how to find it? How to find that depth? So remember the collapse, right? Again, I'm going to plot it here, right? And let's say this is depth, right? And this is pressure, which is hydrostatic pressure, right? And hydrostatic pressure of the mud, which is outside. And this is basically equal to your collapse pressure, right? All right, collapse pressure at the surface, 0, no hydrostatic in the annulus, right? And it increases based on the density of your mud all the way to 8,000 feet, right? Now, how can I find the depths at which this 4,760 psi can resist the collapse requirement? How can I find that? Any idea?
Treat H as a variable in your hydrostatic pressure equation and set it equal to the lower one.
Okay, so you mean that I put the 4,760 on the right-hand side, right? and then say 0.052 multiplied by 12.5 multiplied by H, right? So what it means is that I have a casing that its collapse resistance is 4,760 PSI, right? Now, what depths I do have a 4,760 PSI collapse pressure, which makes it equal to the rating of my casing, right? So this is collapse pressure, right? And my collapse rating is 4,760 for this lower weight casing, right? So I want to see what depths that is. And if I want to do that, I just do this, right? This is the hydrostatic pressure equation, and I want to be my pressure to be 4,760. So what is my depths, right? So I should say that this pressure is how much? 5,850. Why? Because that is at 8,000 feet, right? That's what my worst case scenario collapse pressure is at the bottom of the wellbore, right? Okay, so if you do that, that doesn't work. I mean, that works, but you have to also consider your design factor, right? So you have to divide your collapse rating by your design factor first. So I shouldn't look for this because my collapse rating is 4,760. That's true, but the problem is that I have to also I shouldn't design for 760 PSI. I should design for 760 divided by 1.125. And that gives me the depths, right? And if you look at it based on the equation, you always put that design factor here. So you should have that 1.125 on the right-hand side, which you have to take it to the left, right? So now, if I do that, if I divide 4,760 PSI divided by 1.125, that's 4,231. So this point is 4,231 PSI. And I want to find what depths it is. Is it clear so far? Any part that is not clear? Any questions? All right. So if no questions, then we can find that depth, right? Simply just by using the hydrostatic pressure equation. So that's 6,509 feet. And that means that you can set, you have a wellbore, right? And then you have a 47 pound per feet casing. I'm trying to kind of make it different. That is equal to 6,509 47 pound per feet casing, and then I have another casing which is 53.5. The rest all the way to 8,000 feet. Are we done? Do you guys think that now everything works perfectly fine and we are ready to go to the next step, which is tension check? Well, we are not done. Why? Because the way you designed the length of this 47 pound per feet was based on the collapse rating based on 0 axial tension, right? Did you consider the axial tension? No, you didn't, right? And if you remember, for the collapse particularly, the axial tension changes your collapse rating. But what you designed right now is based on the 0 axial tension. So what should you do? How much axial tension do you have now on 47 pound per feet casing at this point? How much axial tension do we have? Any idea? You guys know it. You did the homework for axial tension. How do you calculate the axial tension at this point?
Is it the weight of the pipe minus the whatever the buoyancy force would be?
Well, for the collapse, that's a good weight. First, yeah, it's the weight of this casing, which is hanged over that point, right? That's what you need to calculate. So that's 53.5 pound per feet multiplied by the length, which is 8,000 minus 6509, right? That's the weight of that casing that is hanged from that point, right? But for the collapse design, we don't consider the buoyancy. We just assume that it's an air weight. Again, that's the worst case scenario. Okay, so the actual tension that you have is just 53.5. You don't consider the buoyancy. It's just the air weight of the casing. And that is 53.5 multiplied by the length of that 53.5 casing, right? That's how much actual tension is being applied to the bottom of 47 pound per feet casing. Okay, so it's not zero, obviously, right? But we designed it for zero, so we have to redesign that. Okay, so how do we redesign? We have to calculate a new collapse rating for the 47 pound per feet casing based on the actual tension that is being applied to that. Okay, how do we do that? Well, we first calculate that weight, which is this much, right? Did we? Yeah, here is they're considering this is considered with the buoyed weight, with the buoyancy, but I believe we shouldn't consider that. That's okay if you did that too, but let me see. Yeah, for the design, assume no buoyancy effect. That's what we mentioned, right? So I think we shouldn't consider that, but that's fine. Either way, it's okay if you did that, but this is buoyancy factor. How do you calculate the buoyancy factor? One minus density of fluid divided by density of steel. That's the buoyancy factor if you go back to the slides of the axial tension. So that's 1 minus 12.5 over 65.4. This is the density of the steel in pound per gallon. And this is your mod weight. Now, as I said, I shouldn't have put this 0.809 in here, but that's okay if you did that too. This is the weight of the casing, which is hanged, right? And this is 8,000 minus 6,509, right? And then multiplied by the buoyancy factor. This gives you this much pound force of axial tension. Make sense? And then you have the axial tension. You divide it by cross-sectional area of which casing? Which cross-sectional area should I use? Should I use the 47 pound per feet cross-sectional area or 53.5?
Probably the 47 because you're measuring from there.
Yes, this force is being applied to 47, right? That's why you have to use 47 cross-sectional area, and that is actually given to you in the table. Plane and area. This means that the cross-sectional area of your steel cross-sectional area, okay? And that is 13.572 inches square. You don't need to calculate it here because this table gives you that number. And in the exam, I'll try to give you that number so you don't need to calculate that, hopefully. Save you some time. But here is that number that we need to use. That's for 47 pound per feet, right? So we need to divide it by 13.572. Now, we are converting the force to a stress, right? This is force, this is a stress. This is in unit of pressure, this is in unit of force, right? And to do that, you need to divide your force by cross-sectional area of the casing. That gives you how much PSI of stress is being applied to that 47 pound per feet casing. Now, based on this stress, you can calculate what? You can calculate a new, before going here, before talking about that, you need to calculate a new yield strength for your pipe, for 47 pound per feet pipe. Why? Because there is a 4,700 PSI stress being applied to that casing. And that casing was N80, right? That means that your current yield strength, minimum yield strength, is 80,000 PSI, 1 minus 0.75, the stress that is being applied to that casing, divided by yield strength, and you are getting 77,517 PSI. That means that now the casing is not basically 80,000 PSI minimum yield strength, but it is 77,000 equivalent, basically yield strengths. Does it make sense so far? Any questions? All right, so we calculated this. Now we need to calculate a new collapse rating for our casing. We cannot use tables anymore. And the reason is that the tables only give us the collapse rating when you have zero axial tension, but you don't have zero axial tension now, right? That's why we had to calculate an equivalent yield strength. And then you need to decide which type of collapse are you in. Are you in the yield strength collapse, plastic, transition, or elastic, right? And that is calculated based on the outer diameter to the thickness ratio. Remember, we talked about this, right? And if you go to the tables, I'm not sure if we have it here. No, this is a short table, so it doesn't show everything, but we can go here to the N80 casing, and that is 9 5/8, right? Go back up to the example. That is 9 5/8 N80 casing, right? So I'm gonna go back here to the page that we were initially. And I'm gonna go to the book, 9 5/8 casing. Every 2 pages, these 2 pages, if you open the book, you see that they are in front of each other. So they are the same tables. But anyway, here we have N80 casings, right? 9 5/8. Thickness is given to us for 47 that we are interested in, 0.472. And the outer diameter is, of course, 9 5/8 inch. Divide that number by the thickness. That's the D/T ratio, right? And then you know that 5/8 is how much? 0.625. Let me double check that. 5 divided by 8 is 0.625. So this is actually 9.625 inches. You divide it by 0.472. That is D/T ratio. Make sense? So once you calculate D/T ratio, for this specific casing, I think it's given to us. This is 20.39. If you divide these two numbers to each other, 20.39, you should see where it falls. Is it less than this, between these two numbers, or between these two numbers? These are based on the API tables, which I haven't still shared it with you. Once I assign the homework, I'll share these tables with you as well. And for N80 casing, based on this table, 20 is in, I should look at this number, but it's still here. N80, that's 20 for us, right? So it's a plastic collapse that we need to use the equations for, right? So plastic collapse, the equation for plastic collapse is this equation. Again, if you refer to slides, you'll see this equation. So you need A, B, C, right? And then you refer to the collapse table. Let me see which one is plastic collapse is the same table that we were in. For N80 casing, L and N AD casings, A, B, C given to us, right? So we use A and B and C. We have the D/T ratio, 20.39. We have the new equivalent yield strength, which is 77,000. So we set it there. 77,000, A, B, C, D over T ratio 20.39. Calculate the new collapse rating, which is 4,008 PSI. Now, well, with the design factor divided by the design factor, that's 4,008, right? Now, compare it with whatever was initially, 4,750 PSI. They are different, right? So what you need to do is now design based on this. I mean, find the depths, find the new depths based on the new collapse rating. How much you were initially? You were at 6,509, right? Feet. And here is 8,000 feet. And this is 47. And this is 53. Now, how do we find the new depths? Same method, exactly. P is equal to 0.052. This is with the design factor. Density H. Pressure is with the design factor again, 4,008. 0.052. Density height. If you do that, your new height is 6,166. So it's basically, oh, sorry. Views. Let me fix this. Page display, single page. Okay. So 6,166. So you are actually, your casing should be here, the 47, not there. 6,166. And the rest should be 53. So now my depth is not here anymore. This is 53 pound per feet. This is 47 pound per feet. Are we done here? Do you guys think that we are done with the design of collapse?
Yes.
All right. Others? Everybody thinks that we are done with the collapse because we calculated the new depths based on the axial tension.
Probably not, because you're asking.
That's right. Why not then? What has changed in terms of design parameters for your collapse? Anything has changed from the previous set depths, which was 6,509, and now your set depth is 6,166.
Axial tension.
Axial tension has changed now, right? So since your axial tension has changed, you need to redo the design because your axial tension is not the same anymore. Now you have to design based on this length of 53 pound per feet. So we do this process completely again, okay? So again, calculate the weight, 8,000 minus 6,166 multiplied by 53 pound per feet. This multiplied by buoyancy factor is equal to 79,000 pound force divided by cross-sectional area of 47 pound per feet casing. That is 5,861 PSI actual stress being applied to 47. And then we need to calculate a new yield strength for our casing. So that's 80,000, 1 minus 0.75, the new value of stress. And then this is 76,000. You remember previous one was 77,000 something, right? Now the new equivalent yield strength is 76,000. Again, we are in the plastic collapse because our D over T ratio has not changed. It's the same, right? So we use the same equation, 76,000 this time. A, B, C, D over T ratio. you get the new collapse rating, which is 4,458. You divide it by design factor, you get 3,963 psi. Now we need to find the depths at which we have 3,963 psi. So what depths again? Yeah, let's go back there. What depths do we have that 3,963 psi? This is wrong. This should be 3,963. Okay, let me see if the numbers are also wrong here. That should be 3,960 divided by 0.052 divided by 12.5. That's 6,096. So the number is correct, but this number is basically written. So this is correct, but this should be 3,963 psi, right? Now, your casing depth now has changed to 6,096 feet from 6,166 feet, right? What should you do now? You should redo the calculation, right? Because that depth, because your axial tension again changed here, right? So we do it again. Now, based on the 6,096 feet, calculate the weight of the void weight of the casing here in this case, divided by cross-sectional area, get the stress that being applied, calculate a new value for minimum yield strength, equivalent minimum yield strength, 76,791. Find what equation you need to use because outer diameter to thickness haven't changed. Use the plastic collapse equation, but this time with 76,000 yield strength. Calculate the new collapse rating divided by 1.125 design factor, 3,955. I don't know why these numbers are messed up here. And let me see if I get what number here. 3,953 divided by 0.052 divided by 12.5. That's 6,081. So this is not correct. Okay. So what should you do then? How much is the difference? Is around 15 feet, right? So you see that the difference between these points that you're setting the casing are actually dropping as you do different iterations, right? So you started at 6,500 for the set depths, right? And then you went to 6,100 something. Then you came to 6,906, and then you came to 6,081, right? Probably if you do one more iteration, you'll be done. Or if that's satisfying for you, that's enough. You can stop depending on if I ask you to do that or not in the exam or in the homework. Basically try to reduce this difference between two set depths of two iterations. Let me see if I did another one. No, I didn't do another one, but 3 iterations here. And that's now we are done really. We have set the casing depths of 47 pounds per feet, right? By multiple iterations. And the reason for iteration again is that you have different axial tension each time you do these calculations. So you need to redo the calculations, right? And that's it. That's how you design for collapse for these two casings. Any questions here?
Could you do like a goal seek on Excel?
Yeah, there are ways to do that for sure. You can do it probably, yeah. You can also write a code in Python to do that. For the homework, I will ask you to do it by hand because I want you to get familiar. But if you also wrote a code that does that for you, then that's also okay. Because that means that you understood the problem, right? So Yeah, so you did design for any other questions here? All right, so you're not done with your casing design, right? Can you use the other casings, the first two again for the burst? You cannot, right? Because those two did not satisfy the burst requirement. So we just ignored them completely. Okay. Now this is our casing now. And the problem here is that this is how we basically started from 6,500, 6,196. And this was not accurately 96, right? But anyway, let's assume that we are there, right? And now we need to check for the tension at the surface. How much tension is being applied? At the surface.
Zero?
Zero. Why?
Because he started from the surface.
Well, you should see when you do the actual tension calculations, you cut the pipe, right, and hang it with your hand. Do you feel zero force? Cut the pipe at the surface from the surface, whatever is hanged to, right? And just try to hold it yourself. How much tension do you feel? Zero?
No.
No, you feel the whole weight of this casing, right? You have to take all these casings, right? So you have 6,096, let's say, of 53 pounds per feet, 53.5, plus, no, the difference, this is not correct. This is 8,000 minus 6,996 multiplied by that. And then the rest, which is 6,996, is 47 pounds per feet. So that will be your tension multiplied by buoyancy factor, right? And that is the same as buoyancy factor we used previously. And that is 313,000 pounds being applied. Why do we check at the surface? Because that's the highest tension in the system. The surface is the highest tension. The bottom of your wellbore is the highest collapse, and burst is the same all over in your casing. Okay, so we check the surface always. We calculate this. We multiply it also by your design factor, which is 1.8. That makes it 563,000. And then you check your 95847 casing, which is at the surface, right? And what you need to check is this number, pipe body yield strength in thousands. Now, if I go all the way there, that is 1,086 multiplied by 1,000. So that's 1 million pound force that this casing can resist. How much is this one? 500,000. Perfect. We're good. Far away from the failure, right? With the design factor. So that's done. That's it. So it meets the casing tension check as well, right? So burst, okay. Collapse, okay. Tension, okay. And we are done. That's the casing design. We designed most economical. Of course, you could use 53 from the surface all the way to the bottom, right? And you didn't fail any of these three, but that was more expensive. That's not the best design. The reason is that 53 is more expensive than 47. So you want to put the 47 casing to some specific depths. And that's what we did. Any questions?
So do you compare the 563 705 to the table? So what do you do?
Yeah. So this is 563. Our rate on the table is 1 million something, right? So the rating of the tension of the casing 47 is much higher than the worst case scenario tension that will be applied to the casing. And therefore, we are okay at the surface. And that's the only point you need to check for this tension.
So if it's that number is higher than that, will be
You fail. What you do, well, this question I ask you, can we use 43.5? We cannot, right? The reason being that you don't meet the burst requirement. I'll be back. I'll go back to that one. But if you fail the tension, you want to reduce the size of your, that one remedy is to reduce the size of 47 pound per feet. And at the top, use 53.5 pound per feet casing, because this one has higher tension requirements. So if I go to the 53, which is at the bottom, you see 53 have higher tension resistance compared to 47. If you failed in some specific design that you may fail, I think, in your homework, what you want to do is you want to use the higher grade casing to some specific depths at the top. In the middle, you use 47. And again, at the bottom, use 53 pound per feet. Okay. So now you see how complex it can get, right? If you want to make it even more complex, assume that your pore pressure was not 6,000, but it was 5,500, and then your burst requirement was 6,050. And then since the burst rating of 43 pound per feet casing also satisfies the burst requirement, then you need to design for 3 casings, not 2 casings only. So you need to design the 53, 47, and 43.5. So that's a 3 casing grades in one wellbore, right? How do you design for that? All the designs that we do, it's a bottom to top approach. So you design for the bottom first, right? So you say initially, remember, for the burst, we said, okay, I'm going to put the 53 from the bottom all the way to the surface. And then you said, 47 also satisfies my burst requirement. So let's find the depths for 47. You do that, the length of the 47. Once you decide about that length, you do the design for 43. So 3 steps of the design from bottom to the top approach, basically.
That would be 2 iterations for that design, right?
Well, you don't know. You have to iterate until these steps doesn't change. But yeah, here you see that it's only 2 iterations. That's the initial, and then initial one that you just calculate, no iteration here, but first iteration, second iteration.
I meant like 2 sets of iterations, because you have.
Oh, yeah. 2 sets of iteration. 1 set for this casing, 1 set of iterations for this one. How many iterations you do, it depends if this steps, this length of the casing that you design doesn't change anymore after 2 consecutive iterations. So that's how you do it. Make sense? Any questions? Well, here is the review. You can go ahead and read it, all the steps that we did to basically do the problem. It's reviewed here. I'll post the homework today. So start doing the homework. We will have another casing design slides talking about it on Wednesday and Friday. But we just talk about specific casings, surface, intermediate, and production casings. But as far as the design, you can start doing it now. You don't need to have the other basically slides to do the design. And yep, that's it. That's kind of the most complex calculation so far we had, I guess. Any questions, anything?